All right, we're back. We're on page 13 of note 17 of Calc C. We're talking about polar areas. We just went through a problem really similar to the one we're about to do. So I'm going to do this one a little more quickly. If you find it a little confusing, head back and watch that video again, and it should help you out. So to find the inner loop, I'm going to set r equal to 0 and get cosine is -1/2, which means that theta is 2 pi over 3 or 4 pi over 3. And then I'm going to graph the rectangular just to get a sense of what's happening. So here's 8. I can go up to 24. I can go down to -8. It's cosine and it's positive. So it's going to be like this. Oh, I didn't finish. There, to there, to there, to there. So your inner loop happens here. It's the dip. And we just figured out when the dip happens. It happens at 2 pi over 3, and then it ends at 4 pi over 3. So how does this work on the graph? Well, you start at 0 when you're here. You go all the way around. Here's pi over 2. And then as you get to 2 pi over 3, boom, you're going to start your inner loop. 2 pi over 3 to pi. R is negative throughout. That's why you're graphing on the wrong side of the y-axis. Pi, you're here, and then 4 pi over 3, you're going to end your inner loop. So if I go 2 pi over 3 to 4 pi over 3, it's going to give me the whole thing. I could also go 2 pi over 3 to pi and double it, which is my preference. So I'm going to do that. So 2, 1/2, 2 pi over 3 to pi of r squared d theta. You can also just go 1/2 and then 2 pi over 3 to 4 pi over 3, and it'll give you the whole thing. It's like a good choice either way. Between the loops, I think the right thing to do is first find the total area. So total area, for this one's actually a little bit easier, right? Let's just go 0 to 2 pi over 3. We'll have filled in all of this, which is definitely half of it, and then we'll just double it. So I'm going to go 2, 1/2, the integral from 0 to 2 pi over 3 of r squared d theta. And then between the loops, so I'm going to call this a sub 1, I'm going to call this c sub 1. I just don't like calling them a and c. I don't really know why. But like the little subscript, I feel like makes it all work out. So here we're just going to do c1 minus a1. And all right, calculator, let's do it. Let's do it on calculator. Let's get them. Switching. All right, step 1. I'm gonna do new problem. Doc 4.1, calculator page. Definitely in radians. Gotta be in radians. Store your functions. 8 plus 16 cosine of t. All right, so 2 times 1/2 is just gone, so I'm not gonna type it now that I messed that up. Integral 2 pi over 3 to pi of r of t squared dt decimal. 34 point, that's really big. Oh yeah, it's like half of an 8 by 8 square kind of, so it sort of makes sense to me. So 34.785. So I wrote that in. I've also highlighted it because it's kind of bleeding into other things. So there we go. And then we also thought that we could just do 1/2 the integral of r of t squared comma t if we went from 2 pi over 3 to 4 pi over 3. I think it will give you the same answer. And it does. You definitely want to try to do that. You want to check your understanding by trying to do it in multiple ways. Good plan. I'm going to get the answer to C. Integral of r of t squared comma t from 0 to 2 pi over 3. And so it was 2 and 1/2. So 5, huge number, 568.401. 401, and then I should do this minus this. It's 533.616. 533.616. And that's it. So I didn't actually work out another way that I could get the total area. I think you could get the total area let me go back to, well, let me like see if I can work it out. So I want to go backwards to negative, I think I want to go negative 2 pi over 3 to 2 pi over 3. So I think I want to do 1/2 integral r of t squared t negative 2 pi over 3 to 2 pi over 3. I think that'll give me the whole area. 568.401. Woo! Okay, let me go back to the notes and I'll show you why I thought that was going to work. So part of why I thought that would work is that I spend a lot of time graphing polar things. And so like the graphs and the symmetry and things like that, like kind of, you know, they make sense after a while. What I was thinking was, I want to rewind, right? And rewinding to negative pi over 2 is not enough. I want to keep rewinding. But like by symmetry, if I had to go forward to 2 pi over 3, it makes sense that I would want to rewind to negative 2 pi over 3. So I did that. I'm starting at negative 2 pi over 3, going to 0, going to 2 pi over 3. Boom, total area. So definitely the more you graph in polar, the easier those kinds of things get. And initially they just kind of look like magic when people are doing them, but they're not. It's just people doing things that make sense. All right. For the curve r equals 2 minus 4 sine of 2 theta. I like this curve. It looks neat. It's like almost a rose curve, but like the petals aren't all the same. Very cool. Find the area enclosed by the large propellers. So the total area, so I mean, I'm probably gonna like find one and double it or something. Find the area enclosed by the small propellers, sure. And then find the total area with what? Just one integral. Okay. I have some ideas, I think. So first, it would be really helpful if I had a graph of the rectangular thing, which I will put down here. So it's, well, maybe I should put it like accurately-ish. So we're at 2, go up to 6, go to negative 2. So let's see if by graphing this, we can kind of like figure out what's happening. So the period of this is pi. So I don't even know. I think it probably takes 2 pi to do the whole thing, but it might take 4 pi because of the 2 theta. So 2 pi, there. Let's graph it. It's a negative sine. All right, can we see how this relates? So 0 to whatever gives me this little sliver, right? Just this sliver thing right here. That's 0 to whatever. And then from whatever to whatever, I'm going to get this, which is kind of like an inner loop, but it's actually a small petal. So I'm going to highlight. So this right here is this part. And then I need a big petal. So I don't really have one full big petal graphed yet. I need to keep going. So let's go to 4 pi, and then 3 pi, and blah, blah, blah. Mostly I'm blah, blah, blahing because I never worked out what I needed. 2 pi, wait a second. This period, the period of this thing is pi, not 2 pi. So I actually do only need to go to 2 pi because I need 2 full periods, but each period is pi. And that would, because I never worked anything out, that's like a super easy fix. It's kind of like cheating. Here to here, to here, to here. Okay, so I see one big full petal. This, which I call the propeller, I guess. So it's just going to be a trig problem at this point. Like this is really like a pre-calc type trig problem. So the thing that I've highlighted there is this propeller. Unsteady hand. It's so sad. Yeah. So you got to go like a little past pi, I guess. Yeah, part of it is that I don't like this overlapping thing that it does. And so I always try to do it in one shot, and it like increases my general stress level about tracing things. So it's gonna be a little past pi. And if you look at the graph, you're definitely going a little, here's pi, and go a little past. All right, I think we can do definitely A and B. Then I got to think a little more about C. I think what I'd want to do is, like here's 0. If I rewind to here, You know, actually, we could just do 0 to 2 pi. It never covers the same area twice, right? It's not like inner loop and then like giant outer loop. So we can just go 0 to 2 pi. That's actually going to be the most straightforward part. I need the zeros. So if r equals 0, then sine of 2 theta is going to be 1/2. So 2 theta is pi over 6, 5 pi over 6. I want to keep going because theta is between 0 and 2 pi, so I need to go to like 4 pi so that I can divide them by 2 and get them back in. So 12, so 13 pi over 6, and then 17 pi. So I just added 2 pi. Add 2 pi to this in the form of 12 pi over 6, then add 2 pi to this in the form of 12 pi over 6. You get those, which means that theta is pi over 12, 5 pi over 12, 13 pi over 12, which is a little bit past pi, which makes sense to me, and 17 pi over 12. Okay, so this first one is, so down, I'm looking down here. This is pi over 12, this is 5 pi over 12. So for, that's a small propeller. So I'm gonna do that first, I guess. So there's 2 small propellers, each of which has area 1/2 pi over 12 to 5 pi over 12 of r squared d theta. That should do it. There's 2 propellers. Each one goes from, well, they don't both go from pi over 12 to 5 pi over 12. It's actually like 0, start at pi over 12 to 5 pi over 12. Nothing. 13 pi over 12, you're going to start and go to 17 pi over 12. You're done. And then nothing. This is 17 pi over 12 to 2 pi. So, all right. Big propeller. Big propeller is going to go, here's 5 pi over 12, keep going. No, it isn't. This is pi over 12, keep going. 5 pi over 12 is when it starts. 13 pi over 12 is when it stops, and there's 2 of them. So we're going to go 2, 1/2, the integral from 5 pi over 12 to 13 pi over 12. Knowing that it's like a little bit past pi has really helped me be like sure of what I'm doing. I'm writing this in the entirely wrong spot. Up here. Eyes up here, buddy. All right. Find the total area with just one integral. I think that we can just go, I'm going to do 1/2 the integral of 0 to 2 pi because there's nothing doubling r squared d theta. So you actually don't need to be super careful with it. What if I wanted like one weird shot? I'm thinking like I want to back up, right? To negative pi over 2. And then what is this? This is something. Negative pi over 2, and then like another pi over negative pi over 2. Blah. What angle are you? I feel like this is 13. Well, if I just backed up, right? Very far. I want to do, when does this go? This goes at 17 pi over 12 minus, so maybe -7. I think I want to do -7 pi over 12. I'm going to try that. I think -7 pi over 12. And then I would have to keep going. So I backed up, did a full one, there, to 17 pi over 12. I think this will work too. The calculator is going to be the arbiter of that. I think that'll work though. Let's see. So again, key thing, store your function. If you store your function, then you can like do much more easily. R of t is 2 minus 4 sine of 2t. What if I got that wrong? Solve r of t equals 0, comma t, 0 t 2 pi. This will be really disappointing. Okay, no, didn't happen. So I think that the inner propellers, no, the large propellers, sorry, is the integral r of t. I bet this is a really long video. R of t, I just remembered like I did another problem in this video, 13 pi over 12. But hopefully you're finding this just so stimulating. I don't know, 35.525. All right, the small propellers. Let's just borrow this. So we'll make it pi over 12 to 5 pi over 12. And there's two of them, 2 times 1/2, so that cancels. So we get this. And then in theory, if I add those together, this and this, and I've done it right, I should have this answer, integral. I should have borrowed it again. R of t squared, t, you know, do the efficient thing. I think you can just go 0 to 2 pi. Ah, oh, that's so satisfying. Yes, I think we got it. Let's check the other one that I think is a little crazier. Little suspect, negative 7 pi over 12. So try to figure out where I got that value, because I didn't really explain it. It's coterminal to something. That's what I did. 17 pi over 12. Yes. Okay, so I am prepared to say that I think these are answers. So this, I got approximately 37.699. That's fine. The bigger one, I guess, must have been 35.525. The bigger one, 35.525, and then the smaller ones must have added up to 2.174. All right, good work, us. Pretty confident in my answers. I wish I had a whole class here that could tell me that I'm doing something right or wrong. But you know, you make do with what you got, and that's me and my calculator. That's it. So good problem. Gonna stop this here. I will see you in the next one where we're just probably gonna keep going. So see you there.